Thank you. Globally, climate change is the biggest threat facing coral reefs. And without global action, the outlook for reefs and the millions of people who depend on them are grim. But even if we solve climate change tomorrow, many reefs would still be severely threatened by the impacts of overfishing. For example, where I work on Aarhus Island, Papua New Guinea, the reef fisheries all but collapsed. As you can see, it's a small island with a burgeoning population and few livelihood options outside of a fishery that's increasingly integrated into local and global markets. In places like Aarhus Island, getting fisheries management right is what survival depends on. So what could they realistically expect to achieve from implementing different types of reef conservation strategies? What won't they achieve? Having benchmarks is critical because some conservation groups some well-meaning conservation groups can promise the moon from conservation, but when unrealistic expectations aren't achieved, conservation groups can disconnect, local communities can disconnect, sometimes permanently. So these issues touch upon a much larger issue of more clearly defining the benefits and limitations of key reef conservation strategies. Now, we already know that strategies that reduce fishing mortality, such as marine reserves, generally mean there'll be more fish, right? If you stop killing fish, there'll be more fish. But how much more? And when can different types of benefits be maximized? So this parallels a really active and I think important debate in the conservation community right now about the role of conservation in different contexts, and particularly in contexts of areas that are remote and far from people versus areas that are near large populations. And part of the community, the conservation community, would argue that remote areas are really important. They're like critical last vestiges of marine wilderness and need to be protected. And others would argue that, well, often protection in remote areas is just token anyway, and resources, time, and energy from conservation could be better spent in areas that are more heavily impacted by human presence, and you get a bigger sort of conservation gain from doing that. But to date, the amount and types of benefits provided by reserves or marine conservation in different contexts has yet to be quantified. So what I want to share with you today is an effort I've been leading over the last 5 years to generate insights into these and other questions by studying coral reef social ecological systems at a global scale. I've been leading a working group of nearly 40 scientists from a range of disciplines. And we've studied nearly 1,800 tropical reefs across some 41 countries, states, and territories that represent an extremely large gradient of things like socioeconomic development. So for example, going from some of the poorest countries in the world to some of the wealthiest, population and market integration. So the question we're asking today is how do conservation outcomes depend on human pressure in the surrounding seascape? Now, we classified our study sites into 3 broad types of management. These included openly fished sites, which are basically sites that lack effective fisheries management. These were, in a sense, are counterfactual, right? This is what would happen in a given set of conditions if we didn't manage things. We looked at sites that had restricted gear or access. So they might have banned things like spear guns, or they might have banned certain types of net fishing, or they had arrangements that didn't allow other people to come fishing on the fishing grounds. And then we also looked at high compliance marine reserves. Now, I'm the first person to tell you guys that not all marine reserves are high compliance. And for this case, what we did is we had our data providers separate reserves into those that they knew were effective, had effective enforcement and compliance, and those that didn't. And we discarded the ones that weren't high compliance because we weren't interested in how well things that weren't working were working, if you follow me. So we looked at 2 broad types of conservation outcomes. Right? We looked at the amount of fish on reef, fish biomass, and as a social scientist, this is actually an important indicator of what's available for people to kill and eat. So this is a really important indicator from my perspective. We also looked at the presence of top predators. So these included serranids, carangids, and luginids over 50 centimeters, and sharks. So to look at human pressure, we used something that every one of us is familiar with every minute of every day, and unless you're an astronaut. But if you're that, you're in the wrong center of excellence. So, but this is the notion of gravity. And if you guys remember from high school physics, right, the gravitational pull is the mass of something divided by the distance squared. That's the gravitational pull of 2 objects. Well, economists and geographers have been using the same concept, right, to study trade and migration flows between two cities or two countries since the 1880s, and it's often been called the most successful model in economics, but hasn't really been applied in a natural resource context. So we developed a gravity metric that captures potential interactions with reefs based on the size and accessibility of the nearest city. And this was the sort of port or provincial capital. And this was to really gather the sort of market interactions. And you could almost imagine a city being a sort of a black hole vacuuming fish off a reef from a given distance. And one thing that I just want to emphasize that we did is we used population divided by the travel time squared rather than distance squared, straight distance. And to measure travel time, we took global land cover data, so whether it was there was a swamp or a forest or anything like that, we had roads, we had all the global land cover data. And there's actually estimates of travel time. How long does it take to get through a swamp? How long does it take to get through a forest, a grassland? How long does it take to, on average, a road? And we were actually able to calculate for each reef how long it took. We calculated every possible route that you could go and figured out the least cost route to go between a reef and the nearest city, right? And I just want to emphasize here, this is Kimby Bay, and we looked at two reefs there. One point A, which is shorter as the crow flies, but takes longer to get to than point B, which is longer as the crow flies, but easier to get to using the transportation networks. And the point here is that typically most people use as the crow flies measures, but what we found was as the crow flies isn't particularly helpful unless you're a crow. So we also looked at the gravity of the nearest settlement, and this was any sort of human settlement that was there, no matter how large or small it was. It was the closest settlement, and this was to gather something about sort of subsistence use. So we had sort of an idea of market use and subsistence use. We also did this for every populated cell within 500 kilometers. So we drew a radius around the reef, and everywhere there was a populated cell, we figured out the least cost distance to get between there and the reef, and we summed that up. So this is kind of what we'll call total gravity. And this is what I want to talk about today. This is what I'm going to talk about, but we've used the other ones in other papers that we've done. So my PhD student, Ava, who's a co-tutel student between here and University of Montpellier, calculated this gravity metric for every single coral reef globally. So this took a supercomputer so long. If you could imagine for every reef, calculating every populated cell and every potential way that you could get between there and summing that up, it was an amazing feat. It's actually available free for download there and is part of the paper that I'll show you guys the link to a little bit later. But one of the cool things we were able to do for visualization purposes was actually put some vertical relief on there. So you can sort of see the difference between the places we've been talking about today, the sort of Great Barrier Reef and the Coral Sea, relative to places like Southeast Asia and the Caribbean. And just, you know, the seascape of gravity is just fundamentally different in these places. So this here's the graph between gravity and biomass. We've got gravity ranging from low human pressure to high human pressure, and our y-axis there is fish biomass. So basically no fish on the bottom, lots of fish on the top. So these are our country-level averages for openly fished sites, and they're scaled, the bubbles are scaled by the relative sample size in that country or state, right? So the small dots, there's relatively few samples, and the larger dots, there's a lot more samples there. Now, I want to point out that these are the marginal relationships, accounting for things like sampling type, sampling area, depth, habitat, productivity, climate stress. These are what I call the nuisance parameters. They're things that I'm not at all interested in, but I have to account for. And also things like human development, national population size, local population growth, and what we'll see in just a moment, we'll get to in a bit, is reserve age as well. We've accounted for that. So this is where Aarhus Island would sit, in the place that I work. That's it's obviously not its own country, but that's where it would sit if we were to aggregate it there. So this is the same graph, and I'm just gonna leave it up there for a little bit as I draw the trend lines and compare them. So that's the trend line there for openly fished sites. For restricted fishing, we see there, so there's slightly more biomass in all instances where when you've got restricted fishings, right? When you ban certain gears or you ban the access to it. Not too much, but a little bit more. And then when we look at high compliance reserves, we see those are actually quite a bit different. So let's take a look and zoom in on those, on these trends. And what we see is that reserves mediate, but not eliminate key human impacts on coral reefs. So if we were just to draw a straight line out from the remote reserves, we'd see that the amount of fish biomass in remote reserves relative to reserves that are near people is about 4 times more fish biomass. So in other words, if reserves that are near lots of people can only gain, on average, about 1/4 of the fish biomass of those in remote areas. So what about for top predators? Well, we only encountered top predators on 28% of the reefs we surveyed. And we were 100 times more likely to see top predators in low versus high gravity reserves. Now, it was a relatively similar pattern for restricted fishing, and we hardly ever encountered top predators in reefs that weren't protected, regardless of how remote they were. Now, one of the real interesting things here is that in high gravity situations, there's actually really little difference. No matter what type of management you got, you're very unlikely to see a top predator in any type of management in high gravity situations. But we do see a big difference when gravity is low. That's where you see a bigger difference between doing nothing and having management. So the difference between fished and protected, these are what I call the conservation gains. This is the gain that you would get from having management relative to doing nothing under a certain set of conditions. Depends on the human pressure in the surrounding seascape. Okay, but what about for fish biomass? This one's a little bit trickier, right? It looks like the biggest difference is down below, but pay attention, right? It's on a log scale. So you've got an increasing difference as the units are decreasing. Now, if you can figure out what that looks like, your bigger brain than mine. So what I'm gonna do is just plot the difference in arithmetic units there, right? And that's what it actually looks like. That's the difference between reserves and fished areas, right? And what we see is the conservation gains are actually maximized in medium gravity. That means you get the biggest difference between having a marine reserve and doing nothing in this medium gravity situations. And interestingly, reserves make a bigger difference in high versus low gravity situations. Now, I do want to emphasize that this curve here is when predators are excluded. I'm going to show you a biomass estimate when they're included in just a second. But what we see for the presence of top predators, our probability of encountering a top predator, is the biggest difference between having no management and having reserves occurs in the lowest gravity situations. So when we actually include top predators in our biomass estimates, we see that same curve, but it's just shifted over slightly. The important point here is that the social context in which you can maximize conservation gains differs depending on what your objective is, right? If your objective is to improve fisheries, right, which it may be in many places where I work, that's an important goal of it. You may get the maximum gains in medium gravity, but you can still get really high gains in high gravity situations. If you're interested in encountering top predators, which might be a very important point for many tourism experiences, you want to do that in the lowest gravity situations. Okay, so what about when we're not using reserves? Sometimes reserves are unrealistic options for coastal communities. What about when they've restricted fishing instead? What kind of conservation gains do we get there? Either with or without top predators in the biomass estimates, it doesn't seem to matter much. And likewise, in encountering top predators, the probability of encountering top predators, we see a similar curve. This suggests that gear restrictions can provide incremental gains towards achieving some conservation goals, but that does seem to differ depending on the amount of gravity in the surrounding seascape, right? So you tend to get more benefits from implementing gear-based management, gear restrictions and access restrictions in low relative to high gravity situations. All right, so what about ahus? Let's bring it back to the place where we started. It actually turns out that their options look pretty good. Any sort of management they do, they're sort of in that sweet spot for marine reserves where they'd see the biggest benefit from implementing a marine reserve. They'd also see big benefits from having effective gear-based management there. So if you're interested in reading more about this, or you're interested in more pretty pictures by Tane, you can check out this month's cover of PNAS. And with that, I would just like to say thanks very much to my family. And on that note, so we recently had a baby in September, and I just wanted to say how awesome the center has been, how supportive they've been. I was a little late off the block starting fatherhood, but they've been made the transition really, really easy, and I really appreciate all the support we've had in doing that. Thanks to the SURF team, who've just been awesome at doing all this work, my research group, and of course the colleagues that we've lost along the way, which we'll get to in just a moment as well. So with that, I think I've got time for one short speech disguised as a question, or a couple shorter questions.